Aside from finding the area between curves, integration can be used in finding the volume of the curves generated by rotating your function along the x-axis or the y-axis or a given line. Now, let S be a solid that lies between x equal to a and x equal to b. If the cross-sectional area of S in the plane px through x and perpendicular to the x-axis is a of x, then finding the volume of that figure will be given or will be computed using this formula, which is v equal to ax dx from a through b. Now, the idea of finding or computing for the volume of a solid figure generated by rotating the function along an axis is something similar to this solid figure. So this solid figure right here is, of course, a cube or just a pile of paper on top of each other. Now, to find the volume of this particular figure, what we need to do using calculus is to just use a slice, and that slice right here is a piece of this solid figure, and we're going to find the volume of the solid figure by using this single slice of or from this pile of paper. And we will use integration by finding or computing for the volume of this solid figure for today. So in calculus, we're using function, we're not using paper. So in this particular example, let's find the volume of the solid obtained by rotating about the x-axis, the region under the curve of y equals square root of x from 0 to 1. Now, if we're going to graph the function and follow the instruction in the example, we are going to generate this particular graph, which is the graph of y equals the square root of x, given by the interval 0 to 1. And imagine, so in this particular lesson, you need to be able to visualize what's going on with the figure when you rotate this function right here along the x-axis. So if you continuously rotate this function, it will generate a solid figure similar to this solid figure. And this particular solid figure is a cylindrical cone, which we will use in visualizing to find the volume generated by the function rotated or being rotated on the x-axis. Now, just like what I did on my example, so this is your solid figure, and we use a slice from this solid figure, and we will use this slice to generate the estimated volume of this figure. This idea is particularly what we're going to use in finding the volume of this cylindrical cone. And to do that, you can imagine that if we take a slice of this particular solid figure, it will become a circle. So this is one slice of this solid figure, and we're going to concentrate on this particular slice in generating the volume of the solid. So in this slicing, we'll have a circle or generated circle, and we're going to find the area of this slice and use integration to find the volume of all the slices inside this solid figure. And we know that the area of a circle is given by this formula, which is pi r squared. Now, to find r in the area of the square based out of this function, we're going to use the top function minus the bottom function to find the measurement of our radius. And radius in this function will be the top minus bottom, which is the square root of x, the top function minus your bottom function of 0. So our radius is now computed as the square root of x. And we will use this in finding the volume of this cylindrical cone using integration. So this is our solid figure. We took a slice, and from this slice, we generated the radius of the circle, which is square root of x. And we will use this single slice in approximating the volume of your solid figure using the formula ax dx, or integration of ax dx from a through b. And the area that we're working on in this particular problem is the area of a circle, so we're going to use that in finding the integration of the solid figure. So we have pi r squared dx from a through b. And using all the given numbers or numerical values we know in the problem, the volume will then be integration of pi times the square root of x, which is our radius, squared dx from the interval 0 to 1. And by evaluating your function, We know that pi is a constant, so using the property of integration, we can pull it out from the integral function and concentrate on the integral of x dx. And the integral of x dx from 0 to 1 will give us x squared all over 2 from 0 to 1. And evaluating this integral will give you 1 squared all over 2 times pi. So therefore, the volume of this solid figure being, or the given by the function y equals square root of x rotated along the x-axis is pi over 2 unit cubed. Now to better visualize this particular problem, this is our problem, which is to find the volume of the solid obtained by rotating about the x-axis. The region under the curve of y equals square root of x from 0 to 1. We have our xy plane and our function y equals square root of x given by the interval from 0 to 1. Now you need to imagine rotating the function along the x-axis, and it will generate a cylindrical cone, and from that cylindrical cone we'll be able to generate the radius of that cone, which gives us the square root of x. And from that square root of x we'll be able to find or compute for the volume using a single slice of that cylindrical cone, which is a circle, and the area of a circle is given by the formula pi r squared. Now to find the volume, we're going to generate or compute for that volume using the formula integral of ax dx from a through b. And our formula will be pi r squared, which is the formula of area of a circle. Now, by substitution, our r is pi or square root of x, so we'll have the integral of pi times square root of x squared dx from 0 to 1, which will give us pi x dx, and the integral of that function will give us pi over 2 unit cubed. And that is how we compute for the volume of a given function using integration. Now let's have the second example. So using the idea that we had on example number 1, let's find the volume of this particular solid obtained by rotating the region bounded by the function is y equal to x cubed on y equals 8 and y equals 0 about the y-axis. So imagine this is your function, which is y equals x cubed. Now we are rotating this function along the y-axis. So instead of rotating it along the x-axis like this, we are now rotating the function this way. And if we rotate your function on the y-axis, the solid figure that will be generated will be a cylindrical cone, which is generated on the y-axis. So when that happens, finding our radius is now going to be right minus left. So we're using the right minus left method instead of top minus bottom. And if that's the case of finding the area of a circle, we are going to change the function from y equals x cubed, which is your function with respect to x. We can change it to a function with respect to y, which will give us x equal to the cube root of y. And we know that the radius is right minus left, so the right function is cube root of y minus 0. So now our radius is measured as the cube root of y. Now to find the volume of this cylindrical cone, we're going to take out one of the slices, and we'll have to generate an area of a circle to find the volume of our solid figure. So volume is equal to the area dy from a through b, and using substitution, by using all the information that we have, our limit of integration will be from 0 through 8. And our formula will be pi r squared dy. And our r here is the radius of the circle, which is cube root of y. So we'll have the integral of pi cube root of y squared dy from 0 to 8. And by integration, we're going to find our computed volume for the cylindrical cone as 96 pi all over 5. And by further simplifying this, the volume of the solid can be computed as 60.319 unit cubed.